Okay, so, good morning, everybody. And so today I will give a talk on a recent work of ours, joined with Xinxin, Veronika, and Lei. So this is about zkSNARKs that use elliptic curves and their implementation. So here, so well, what are zkSNARKs? Well, basically it's so it's an acronym for zero knowledge, succinct, non-interactive argument of knowledge. Okay, so it's basically you want to try to convince the prover wants to try to convince a verifier that they know a secret without revealing anything besides this fact that they know a particular secret, so some kind of witness to a language statement. And so the succinctness is because the size is small and of the argument, and then it's so it's non-interactive argument of knowledge, and it has to satisfy three properties: so correctness, soundness, and zero knowledge. So here, so what I wanted to state in this presentation is that so we were working on zero knowledge zkSNARKs that are used basically in Bitcoin transactions, so like zero cash, and these use elliptic curves and pairing computations. And yeah, so I need to introduce a bit about elliptic curves. So elliptic curves, they are an alternative to RSA because of their compactness of basically key size, and also and this is due because there are no fast classical algorithm to break the discrete log on them. And so these zkSNARKs are based on this. Also, their security is based also on the discrete log. So these elliptic curves are quite widespread now, so much so that so here maybe I have something that came out maybe 10 years ago that even now you can draw something using the word elliptic curve. That doesn't mean anything. But okay. So what is an elliptic curve? An elliptic curve is a non-singular cubic equation, and so the points on the elliptic curve over a field F here, they form an abelian group, and this abelian group this is where we are working in. So all the protocol deals with group operation taking place in this abelian group. Okay. So in the case where we deal usually with the prime P here, which with the characteristics of a field of characteristics different from 2 and 3, and in this case the elliptic curve can be reduced to this particular form. And in fact, for the elliptic curves that we are going to look at, in fact, even this A4 prime coefficient is in fact 0. So the elliptic curve is a very special form. This is called J invariant 0 elliptic curve. So the expansive operation on elliptic curves is what is called scalar multiplication. So scalar multiplication is when you have an elliptic curve, say a point of order r, so you're working in a cyclic group of order small r, and then you take a number alpha between 0 and r, you want to calculate alpha times p. So what you're doing is that you write alpha in a binary expansion, and then you're doing this kind of computation here with some corner kind of algorithm. It's also kind of double and add, which is the addition, the additive version of multiplying of square multiplying. Okay. So that's what we do. Normally there are some speed ups that you can use, but what I want to mention is that for zkSNARKs, you need to calculate a large number of such scalar multiplications together, and then add them together. Okay. So this has to do with usually because the way that you calculate, that you use the zkSNARK here is that you form a polynomial out of points in a common reference string, say, and then you form a polynomial from a secret value, and then you basically have well, this would correspond to some point evaluated, well, to some point times a polynomial value. Okay, so this n is pretty large. So typically in this range, so between 10,000 and 1 million. Sorry, 1,000 and 1 million. So, well, of course, what you can do is you can multiply, you can do all the scalar multiplications separately and then add the result together. That's the trivial way, but there are in fact ways to do that much faster. So the one way, if n is not too large, if the number of points is not too large here, is to use what is called Strauss method, which was also rediscovered by Shamir. Yeah, so the point is here. So if you take h is basically log in base q, so q is the power of 2. If you want, think of q equals 2 if you really want. So when c is 1, this is exactly the length of the binary expansion. And and then so you write yeah, so here you want to compute, remember, you want to compute this sum here. Okay, so what you're doing is that first you pre-compute a number of points, which what are these points? These are all the sum of the pi times bi, where bi are just the possible digits in base q. So when q is 2, this is just all the possible sums and differences of bi's. Okay. And then you write a scalar in base q here, and then what you're doing is that in practice, when you compute with Horner's rule, you have to add a point, and then you have to, each time you have to multiply by q, like double and so on. So Strauss method basically batches together all these doublings into a single doubling of all the sum of these things. So what you're doing is that you take say the lowest like the lowest digit in all of these AI PI here. So this is a point like in this form, so it's a pre-computed point, say sigma 0 here, this S0. And then so you add the result together, you multiply everything by q basically, and then you do the same for the other one. So these points here are in fact pre-computing points in this set. Okay, so but this is because the number of pre-computed points scales exponentially with n. This is not good if n becomes large. So another way is to just well, forget about the pre-computed points. So what are we doing then? Pippenger's method. Pippenger's method computes this sigma j's each time, so that these points are not pre-computed anymore, but they are computed using some bucket method. So the idea is to group together in this expression here. You group together all the coefficients which are equal. Say all the coefficients which are 1, all that are 2, and so on and so forth, up to the maximum value for this is q minus 1, right? So you're doing this, and then you when you group together all the pi's with the same coefficient, then you just have to sum all these sums of the pi's times their common coefficient. Okay, and then you do this and you find sigma j. And there is a way where basically it's adult summation or partial summation, where you can compute this in this kind of way. So you see here, you sum each time. Each time you have so this sigma kj, as I was explaining, these are the sum of the pi's corresponding to a single value of the scalar k. And what you're doing is that you're summing in this way. So sigma as j 2 to the c minus 1 appears everywhere. So it appears, in fact, 2 to the c minus 1 times here. So that's, you would have this. So sum 2 to the c minus 2 appears 2 to the c minus 2 times, so and so on and so forth. So, and you can compute these points very easily, because you can just have like a second loop here to compute these points. Pippenger's variant here is like Pippenger, but you batch together the computation. So instead of doing something like that, where you compute these points and then you multiply by q, you compute some other points and so on, it batches together all the q computation, all the powers of q. So the idea is that at this point you don't have only the pi's that have to be pre-computed, but also all the powers of the pi's, all the qj power of the pi. So you have to, so it's kind of trade-off between its memory execution trade-off here. So you store more points. You have to store all these points here. But then the idea is that you don't have to do Horner's algorithm here. You just have one. So as n is just calculated as one such application like this for these points as k here. And now here the sk is like before, is that all the pi's and their powers which have the same coefficient k. Okay. There's also another trick also to reduce the bucket size. So here you see that the possible values of k, they are, well, q minus 1, well, q in fact, but when you're multiplying by k here, when k is large, this takes a bit more time. So the idea is to use the fact that on an elliptic curve, computing the opposite is quite fast, and so instead of using a representation in base q, you use a balanced representation where the bits are between negative q over 2 and q over 2, basically. And then here you have then a sign sum, so plus minus k, where k goes from 0 to q over 2. So this basically allows, and you don't need to pre-compute the plus minus here, these points. We still need to pre-compute the same points, and but your size now is less. Okay, the size of the buckets is less. And Okay, so Luo Fugong then they wrote a paper that extends this method and the Pippenger variant by pre-computing more points in a sense to subdivide a set of possible values k here, which you can call the buckets. So because each bucket corresponds to one, so each bucket is corresponds to one k, and then stores the sum of the values of these points here. So Luo Fugong, they split they write the bucket in a way where you write each value of the bucket multiplier. You split it into basically a multiplier m and the bucket value here. So so for in the case of Pippenger variance, in fact, this multiplier was just one, and the bucket was everything. But in the Luo-Fugong methods, they allow m to be a bit larger and to decrease consequently the value of the bucket here. So by increasing, and what you're doing is then what is that they pre-compute this mij, qj, pi. So you have to pre-compute more points, but the advantage is that the bucket size decreases. So it's not q over 2 anymore, but you have less points to add. And so it's as before. You have a bucket, so some buckets here. So all the possible values of the bucket elements, then in this way, and then you can compute your multiscalar multiplication in this way, where Sk is the sum of the pi's, where the multiplier bij is equal to a single bk. And so then they provide also an analog basically of this Abel summation method. The Abel summation method, in fact, involves well, using some of the SKs, which can be done inductively with some loop. But then you need to also, you have here some delta u, which corresponds to the difference between bucket values here, between consecutive bucket values. So if these consecutive bucket values are small, then this delta u in fact takes place in a, well, it has only a limited number of values, say d values here. So delta equal 1 to d here, and then you can again sum each of these things with this honor scheme here with like the Pippenger variant method, and this is so pretty efficient as well. So the idea of Luo-Fugong is to find a suitable multiplier, a division of your scalars into a multiplier and a bucket set, such that this delta was small. In fact, they find a bucket where d should be at most 6. So here, let's see a bit what we're doing. So Pippenger, the point storage here, the number of points stored is n, because you need to store all the points only, and that's the runtime in curve additions. It's h times n plus q over 2. So h is just the bit size of r in base q. So the q size of r. So in base q. So in the Pippenger variant, you need to store the q to the j times p to the I, right? So you have h powers for q and n points. So you need this point storage. So Luo-Fugong, as we saw, they store also the multiplier times this thing. So remember, you have this thing here. So you have m values for this, h for q, and then n for the points here. So that's the total number of storage. And then you decrease it in this way. So where you have nh plus b. So this is the size of the bucket, and then d is the if you remember, this is the distance between consecutive elements in the buckets. Okay. So they also take a specific example where q is a power of 2, m has size 3. In fact, is a set 1 to 3, and then b is a specific bucket, which we'll see well in the next slide. And d, they claim that it's 4, it's 6. So this is basically quite small, and they find empirically that their bucket size has this asymptotic value. Okay, so q, well, it's basically has positive density about a little bit more than 1/5. But we actually here we strike through this thing, because in fact what we will see is that we found some inconsistencies in their method, and there were some things that were in fact wrong. So this has not to be taken as a benchmark. And once you repair their method, well, there are many ways to repair, but one way that we found is that we just need a slightly more storage. So just there's an expansion which is a little bit longer, but then you come up with a runtime which is proved here, where you have 7/32Q. Now 7/32 is 0.21875. Okay, so it's a bit higher, but there is a reason for that. And then we try to capitalize on this improvement and try to understand a bit better how we can improve this method. So first of all, we understood that there is that you can, in fact, that there is no need to take q as a power of 2. You can take q as a power of a prime, and in particular, when q is a prime, we found a very nice representation here. Actually, q maybe here q is also a power of here q should be a power of a prime. So but anyways, the prime is not 2, and then you find something which is like that. So q, so the prime is small, like 5. I think there was the first example with 5, and so we get something like that also. So we have and we also find that this bucket size is also the best possible. You cannot go below. So it's optimal. We find optimality, and we found some bucket of this size. And finally, one thing that also we discover is that if we use the endomorphism of the elliptic curve, so I will explain that the particular elliptic curve that is used for this for zkSNARKs, so this j equals 0, the j invariant 0 elliptic curve has a particular endomorphism that can be used to reduce the point storage. So instead of basically 3 nh in this case, we have only nh. So the point storage it's divided by 3 with the same performance asymptotically that we would get when capital M has 3 for a bucket 3 size, basically, which was in fact the original Luo-Fugong construction. Okay. So let me just explain a bit what the Luo-Fugong idea was. In fact, it's a very elegant idea. So they start with a set B0 here, which is just 0 and the elements between one, the integer between 1 and q over 2, whose sum of the power of 2 and 3 occurring in their prime factorization is 0. So basically, it's so b is written as 2 to the power something times 3 to the power something times something which is co-prime to 2 and 3, and the exponents have to add up to something which is even. Okay, so they're either both even or both odd. And from this set, so from this set, they remove some elements. So you see here, they remove elements of the form q minus 2i, where I is an element of this set. So it's kind of a strange construction. And also they remove elements q minus 3i, where I is an element of this set. So here, there is this is kind of expect. So here I has to be in the range q over 4 to q over 2 minus 1, which is normal because this element here has to be in the range. So because elements of B are in this range here, q minus 2i has to be in this range here. So it is natural that I will be taken in this range. But here there was something already strange, because instead of taking I up to q over 3, you take it only up to q over 4. And that was something also that we didn't understand in the beginning. Why are you taking up to q over 4? But in fact, there is a reason for that that we discover later. So yeah, so the point then again is they remove elements from B, because what they want is to have a bucket set of size as small as possible. Okay, so we remove as much as possible in order for basically every element to be expressible in one of these two ways. So as a multiplier, so here the multiplier set is 1, 2, 3. So as an element of the multiplier set times a bucket element. Okay. So and they claim that they have that this property is correct. In fact, this is crucial to their argument. But in fact it is incorrect. So you if you take, for instance, q equals 2 to the 10, so 10,034, and t equals 292, and t is in fact this element here, so it's in the set B 0, because the power of 3 is 0 and the power of 2 is 2, so 2 plus 0 is even. Q minus t also is 3 times an element in B0, because again this element here is in B0. And so well, because t is in B and t is equal to q minus 3j with j in B0 here, then we have that t is not in B, because remember that B is constructed from B0 by removing elements of this form here. So because so t is in B0, but it was removed because it's q minus 3j with j in B0. So it's not in B. And in the same way, q minus t is not in B, because q minus t is 3 times an element in B, and it's easy to see that in this case, well, this is not in B. You can just check the sum of power of 3 and 2 is odd. Okay, so this means that in this property, n cannot be 1. So then you check that also in this case as an exercise, n cannot be 2, n cannot be 3. Okay, so it's easy to see. And in fact, what we found is that this property 1 in fact fails in all cases for all q's. It fails for a positive proportion of q. So q, at least q over 216 plus big O of 1 values of t in this range. Okay, so yeah, so they basically remove too many elements from the bucket. Okay, so we try to repair the property. So can we add back a bit more elements so that the property would hold? And yes, so that's what we found. So we basically, first of all, we found out that the property holds for odd t's, okay, which is already not so obvious. So the problem is with the even t's, and what we found is that you just need to add back these even numbers here of the form q. So q here is the power of 2 for them, right? I put it here. So q minus 6i, where I is not in B0, kind of strange inclusion-exclusion thing. And the property holds for all t's here in this new enlarged set here. And also we also checked something that they didn't prove, is that this enlarged set D satisfies D equals 6. Okay, the minimal distance between consecutive elements is almost 6. Something that they also they observed, but they didn't prove in their original paper. Okay, so far. So then we then we try to push the method to a bit more. First of all, to say, okay, how can we improve the bucket size B further? Okay, we have any ideas how to make the bucket smaller? Well, there's an relatively easy cardinality argument that shows that B cannot be too small. Okay, simply because you cannot express all the elements in a certain range as a product of two elements in a very small range. Okay, you don't have enough elements in the product otherwise. So this cardinality argument shows that B has to be at least Q over 2 times the size of the multiplier set. Okay, so in particular, when M is 3, like in here, okay, the size of B is at least Q over 6. Okay. And in so here what we prove is that we can attain these optimal bounds in some cases. In fact, we have an infinite family that we see. So here, for n equal 2, for instance, we have in their setting we can obtain this optimal bound. So first of all, one thing that we do first is that we change Q to a power from a power of 2 to a power of P, where P is any odd prime. So we can do that. Why we can do that? Because these points here, so Q only appears in these pre-computed points here, and these points are pre-computed, so there's no need to have a fast computation of these points here. So there's no need to have Q to being a power of 2, where you can have some speed ups. Okay. So Q, so like for instance, the next slide, Q will be 5, P will be 5, so this will be just a power of 5. So when M is equal to 2, then we have this thing. If P is, say, 5, or in fact any prime which is equal to 5 modulo 8, and then the bucket size 1, 2, then if you construct your buckets to be of this form here, so basically, what are these? These are quadratic residues. It's a power of P times a quadratic residue modulo P, the first half of the quadratic residues, up to P over the power over 2. Then the Luo-Fugong property 1 holds. Okay, and also we have that the size of B is exactly Q minus 1 over 4 plus 1. Note that if P is congruent to 5 modulo 8, then it's congruent to 1 modulo 4, and then Q, power of P, will also go congruent to 1 over to 1 modulo 4. So this is in fact is an integer. Q minus 1 over 4 is an integer. And also D is P. Okay, so even if this power can be pretty large, but the distance between consecutive elements is at most P, so 5, say. If we take P equal 5, then it's at most 5. So that's good. So how can we do better? Well, so in general, one thing which is a bit let's look a bit at the property here. So this property says what? Says that T is MB, or we can write T is Q minus MB. Okay, so this gives a way to decompose T modulo Q, basically, so as MB or minus MB modulo Q, but together with some also some analytic bounds. Like some like you want T to be less than Q, basically between 0 and Q. Okay, so it's a bit so because of that, you need to control somehow the size of B also, because otherwise you are going to have MB could be a multiple of Q, could be large. Okay, and then that would not work. So and then this is a bit complicated because these buckets here have a kind of multiplicative structure. At the same time, you want something which is additively small. Like we saw, this is a bit not easy to achieve. So the easier way is just to say, okay, we'll just do without this bound here. So we will allow a small multiple of Q here. In fact, let's do initially with any multiple of Q. So we have T here. We want to have T equal basically plus or minus MB plus a multiple of Q. So T congruent to epsilon MB, where epsilon is plus or minus 1, and this multiplier and the bucket element modulo Q. So in this case, we forget about the size here. So we lose control on the size of this element. Again, this modification also implies that the bucket size, again, the same cardinality argument, must be at least this. But now, if M is of a particular form, like if we take M to be, say, the first mu integers, like what Wolfgang had before, 1, 2, 3, for instance, then we can achieve the optimal size. In this case, there is a way to control the size, the size of this difference here, modulo Q. So this difference here is going to be at most Q or 2Q. So then with the generalization of the idea that we had before, before we basically had mu equal 1. Okay, so that was a square, so a square modulo P. But in this case, mu is can be something else. So when mu is 3 here, this is a 6 power modulo P. These buckets are basically 6 power times power of P. And then you have that the bucket size is exactly Q over 6 in this case, when M is 3. So it's exactly the optimal bound that we have, that Wolfgang didn't manage to achieve with their buckets. Okay, so that's one thing. And then we say in fact, the whole initially we were trying to understand how we can use endomorphisms of elliptic curves. So in the zkSNARK curve and this Pinocchio curve in particular, and the one used for zero cache, uses this particular elliptic curve. In fact, some elliptic curve of this form for some specific A. Okay? And this curve have a special endomorphism. In fact, there is a special map which changes the point xy to zeta 3xy, where zeta 3 is just a cube root of unity in the field. So if you replace these points in here, you see this is still on the curve because zeta 3 cube is just 1 and y doesn't change. Okay, so if xy satisfies this equation, then this point also satisfies this equation. And now this map here has very special properties. It preserves, it's an endomorphism of the group. Okay, so it preserves the group structure, and so we can, and you see, you can compute it very, very quickly. So we wanted to use this fact somehow. Okay, and so what we found is that you can use this endomorphism omega. So if you think about it here, why are we using epsilon t equals plus or minus 1? Because we remember what I said at the beginning, that the points p and negative p, okay, so the negative p can be computed on the fly when I multiply, so I don't need to store negative p. And so because negative p can be, so negative 1 times p can be computed on the fly, then I just need to store p. Now, in the case of when I use special endomorphism, if I can compute omega times p also on the fly, then I don't need to compute it, to pre-compute it. I can just compute it on the fly, and I can make use of this fact to reduce my bucket size, a bit like was done here, where the bucket size was at most q over 2. And that's what we did in at least so this beginning. So in the beginning, so we generalize. In fact, it's a Pippenger algorithm using these endomorphisms here. In this case, we take m equal 1, so the multiplier to be 1, and this epsilon to be any element in this unit group of the endomorphism ring. Okay, so this omega here can be viewed as a complex integer in this field here in the cube root of unity. So this has 6 units, which are these ones, and we not only using plus or minus 1 now to be computed on the fly, so plus or minus p, but also plus or minus omega p and plus or minus omega squared p. So these can all be computed on the fly, and so we want to then we replace the Lefougon property 1 with the property that for all t in zeta omega, you can write t as a unit times times bt, where bt is it will be some bucket that we have to define, and here we'll just take it equal to 1, like in Pippenger algorithm, okay, to make things simple. And like in Pippenger, as in Pippenger, we only need to store endpoints. Okay? No multiples. So now here, Q will be a power of a prime. So here, because we're going to deal with elements in Z omega, so Q is going to be a power of a prime in Z omega. So this whole congruence will actually happen in the ring Z omega, which is a Euclidean ring. So it's not, well, basically like Z, except that it's complex numbers, some complex numbers. So P in our example, or in our construction, is the prime 2 minus omega, which is a prime about one of the primes above 7. 7 splits into 2 minus omega and 2 minus omega squared. And so we find that we find a result which is similar to the Lefougon result with 1 to 3 here, where you have basically like q to the c over 6. Here we have a bucket size which is optimal, also optimal size, and the buckets are also like before. They are powers of p times beta, where beta is the 6th power modulo p. Okay, and b here is limited in this way. Yeah, so well, things are a bit, so so it looks easy, and in fact, thinking about the what we should prove is not so hard, but proving it is technically more challenging, because you see in the we also need to order the buckets. So there are several challenges, but one of the challenges is to remember in the Luo-Fugong method, we need to the buckets were ordered in increasing order so that the difference between consecutive one was small, right? There was this distance between consecutive values of the buckets that was small. And that's easy to do if you know that all the buckets values are positive and you order them in increasing order. One way you can do it is that you find a subsequence of these B's used, which are spaced by a small value, and then if you add on more values in there, then this is going so the distance between consecutive values is going to be even smaller, right? But because we're dealing here in Z omega, and we don't have control over the argument, if you add values which are not close to the values here, which are like on the opposite side of the that are diametrically opposite, then you have big values. Okay, you have big jump between the values. So we need to control that, and the idea that that we had was to kind of have this web design. Okay, it's not going to be this regular if the disk is if there's a lot of points, it's going to be a bit more regular. But the idea is to have this spiral that spirals inwards here. So these are basically the points. These are the points, in fact, in when k is 0. So the 6th power 1 modulo p here. They in fact they are regularly spaced in a lattice of this form, and then you can, and what you want is to find the Hamiltonian path of these points inside some big disk. Okay, so you have to show that this set has a Hamiltonian path basically, and so in a constructive way, so that you can produce a Hamiltonian path, and that's the construction that we came up with. And so with implementation, well, we found that so our implementation compares pretty well with compared to the repair Luo-Fugong that we did. So the work on the repair Luo-Fugong, it's comparable. It's a bit faster sometimes. Most times, the storage is a little bit higher, but on the other hand, it's a bit faster. What we still need to do is the computation with the endomorphism, that we expect the storage to be really much better, like really 1/3 and 2, and we're still waiting to see what the computation will be. So this is the theoretical computation in the operation, in the curve operation, and then this is the particular implementation in this BLC that was the software that Luo-Fugong also wrote. So that's the actual implementation. So you see that it's pretty fast also. And that's all what I have to say. Okay, thank you very much. So,
any questions?
Any questions?
Yeah, I have a question. Yeah.
Yeah, oh, sorry, I have to share the screen again. Yeah, go ahead.
So, like in lieu of a program method, we put the bucket element in the increasing order.
Yes.
And in the that isogeny method, whatever the last one, yeah,
Yeah, they're not in increasing order. They have this kind of spiral, but the important thing is that this Hamiltonian path has to be constructed so that the difference, each edge has to be small. Okay, the length of each edge in this Hamiltonian path has to be small, because that's basically this difference. This difference between consecutive nodes. Okay, so the views are the nodes here in this path. So the difference of the views is the edge. Okay, and we want the edge to be small. The length of the edge to be small.
Yeah, so we are choosing like the smallest distance between those points. Like if we write the ring elements.
Yes, but you have to be careful, you see, because every point here has different. There are different ones which are close to it, right? So you want to go over them in a smart way, so that you don't have to, at some point, you don't run out of space and you have to jump over some region which was already enumerated. You need a Hamiltonian path, so you cannot go through each node more than once, and you have to go through all the nodes. Okay, so it's a bit challenging, and this disk is not well centered, like the center is a bit off here. So so it's not you're not going to get a regular figure. And in fact, when the disk gets large, the top could be almost flat. Okay, so it's it's not going to be a nice hexagon like here. Okay. Any other question? Yeah, we have to
Thank
leave
you
it.
very much.
Okay, thank you very much.
See you all again in the fall semester, right?
Oh, this was last one.
That was the
Thank
last
you,
one.
everyone.
Bye, Eduardo. Bye, bye, Z. Bye, Christine. Yeah.
I'll see you guys in the next meeting.
Mhm.
Yeah.